Sorry for the late. I have some technical issues. So I can demonstrate my screen and start a lecture. 1 second. If somebody will join us, we will just continue and that's it. So do you see my screen, right?
Yep.
Yeah, okay. So this lecture will be recorded, and if anybody want listen this material, they will be able to see it on YouTube videos or maybe on other platforms, I don't know. So welcome to this lecture of large language models, also known as LLMs. This is part 1 of our deep dive into how these models work, their evaluation and their role in modern artificial intelligence. So here is an outline. Today's plan includes the following points. First, we will introduce large language models and define their fundamental characteristics. Then we will discuss key architectures, starting with BERT, GPT, T5, Bloom, Palm, and Flan T5. We'll cover each model structures, training techniques, data sets, and practical applications. Let's speak about what is large language models. This is models trained on intensive datasets of text. They contain billions of parameters, tunable weights that allow these models to capture the complex structure and patterns in language. By leveraging large amounts of data and significant computation power, large language models can generate text, answer questions, and even mimic human conversation. Let's define large language model, and these models let me see. Yeah, these models are large due to their vast number of parameters, typically in the hundreds of millions to billions. Each parameter adjusts the model's understanding of text in subtle ways. Also, they are trained on massive datasets containing various forms of language, from books to web pages, ensuring a broad and comprehensive language understanding. And because of their scale, large language models can process, understand, and generate human-like language, enabling applications in everything from customer support to content creation. And let's talk about how did we arrive at this point, historical context of this site. So the journey to LLM started with smaller, simpler models. Early language models focused on basic texts, like sentence completion. Over time, as we developed architectures like transformers and began training models on large datasets, we unlocked new capabilities. Transformers developed by Vaswani. Transformers allowed us to model long range dependencies in text more efficiently. paving the way for complex models like BERT and GPT. And we can organize large language models evaluation into 3 branches. It's decoder only models, which focus on generating text, GPT being the most notable example. Also, encoder-only models like BERT, which designed for understanding context in text. And T5 represents its encoder-decoder, and it represents this architecture where the encoder process input and the decoder generates an apportioned output. And these categorizations show us how different tasks are best suited to specific architectures. On this visualization, we can see evaluation of language models from Elm, BERT in the beginning of 2018 and till 2033, and yeah, in the end of the 2033. So do you have questions, or shall we go forward and explain examples of these models?
No questions at the moment.
Okay, thank you. Kim will dive into some major models that have shaped the field. To BERT, an encoder-only model focused on understanding. GPT, a decoder-only model that that generate text. An encoder-decoder model as T5, great for task needing both input understanding and response generations. And also Bloom, Palm, Flan T5. These models introduce multilingual support, large parameter counts, and specialized tuning techniques. So here on this slide, I presented that large language models on this moment can solve a lot of tasks in the same time. And it is the key component of this idea of the large language models. It's different from previous architectures, and on these lectures we will understand how and why they can do so much tasks in the same way, in the same moment. So and here is visualization of what large language models can do. But let's introduce two key architectures. Let's deep a little bit to its details. So let's start with BERT. BERT, or bidirectional encoder representations from transformers, is an encoder-only model that uses a bidirectional approach, looking both forward and backward in text to understand context. And BERT's training tasks include mask language modeling, which in short we can name MLM. Here 15% of tokens in the input are masked. The model tries to predict these masked words, which helps it capture the relationship between words. Also, BERT use next sentence prediction, in short NCP. BERT also learns to determine if one sentence logically follows another, which is crucial for tasks requiring contextual coherence. And let's discuss architectural details of BERT. BERT comes in two main versions. Bird base with 12 layers, and bird large with 24 layers. Each layer has 12 or 16 attention heads, and the model uses GLU as its activation function to capture nonlinear relations. Also, BERT was trained on large-scale datasets, including the book corpus and English Wikipedia using a token vocabulary of 30,000 words through word piece tokenization. I said about it, BERT's architecture allows it to excel in text classification, statement analysis, and question answering. Its bidirectional encoding makes it efficient for understanding sentence relationships, semantic similarity, and named entity recognition. This is examples of what BERT can do, and we see that it's a wide range of tasks, but it can't generate next token. It can't understand what's the highest probability of next token prediction. But it was really useful in that time, and it solved a lot of state-of-the-art tasks which needed to be solved in that time. So let's move to GPT. It's developed by OpenAI, uses a decoder-only transformer architecture. It generates text by predicting the next token in a sequence, making it highly suitable for text generation tasks. Also, this model has versions. GPT has several versions as GPT-1, which is 170 million parameters, initially released in 2018. Let me see, will I have, yeah. I will move to this slide and then we will return to another, to the previous ones. So yeah, I explained that in the 2018, it released the first version, and then in 1 year they released 1.5 billion parameters model GPT-2, offering improved generation quality. GPT third version had 175 billion parameters and demonstrates impressive few-shot learning. And the last version was multimodal model capable of understanding both text and images. Let's go to previous slides and speak about GPT-1 in details. So GPT-1 has 12 layers with 12 attention heads per layer and was trained on massive unlabeled datasets. It uses byte pair encoding for tokenization and handling sequences of up to 512 tokens. GPT in first version training involves a learning rate, a scheduler with linear warm-up followed by cosine decay, and the Adam optimizer. With this approach allows it to generate text that coherent and textuality relevant. Here we can see which tokenizer had GPT-1, and it was trained on book corpora, of which has over 7,000 unpublished books. So here I said that GPT in first version and on second version could predict next token via probability of understanding. So it could solve text generation task, question answering, summarization, and other tasks which could just generate text and allows only on this, but from its 3.5 version, it can solve classification tasks too. It allows a wide range of new tasks, which in previous years solved only on encoder-only models. And just on this moment, we can't understand what was the action which allowed us to have such a wide wide quality, wide amount of the tasks, and such as good quality on them. So we will find out in the next lecture what happened. But now let's move to T5. T5 or text-to-text transformer approaches all tasks as a text-to-text problem. This means every input-output pair from translation to classification is represented in text format, enabling T5 to handle multiply types of tasks within a single unified framework. And let's discuss architecture. T5 uses an encoder-decoder transformer structure. In this setup, the encoder reads the input text embedding and passing through attention layers to capture context here. And the decoder generates the output text step by step, each step influenced by the encoder's contextual encoding. T5 is available in multiple sizes, ranging from base with 220 million parameters to XXL with 11 billion parameters, allowing the flexibility based on computational resources. And training tasks of this model first is span corruption, sorry. T5's pre-training task is known as span corruption. Here, how it works: random spans of text are masked out, and the model is trained to predict these missing spans. Unlike traditional masked language modeling, where single tokens are masked, T5 mask consecutive tokens and enhances its understanding of broader context. This approach helps T5 perform well in understanding long-term dependencies within a text. T5 also utilizes relative positional encoding. We can see this in the training details. Traditional models like BERT uses absolute positional encoding, where each word position in a sentence is fixed. Construct relative positional encoding allows T5 to focus on the relative distance between words. This approach scales better with long text sequences and help the model generalize more effectively, since it can adapt to variations in input length. Let's talk about training data of T5. T5 was trained on the C4 corpus. It's named as colossal clean crowd corpus, which is built from a filtered subset of publicly available web data. C4 ensures high quality data by removing low quality content, duplicates, and irrelevant text, allowing T5 to learn from diverse rich language sources. Do you have questions right now? Yeah, okay. If not, so here it's on this slide we have visualization how T5 works and how it's what is in the input of this model, what is on the output, and also how does it predict this text. And okay, here is one comment that that wouldn't be here. So let's just explain these tasks, what T5 can do. It's the first one is machine translation, summarization, question answering. And we can see that all of these tasks are the same as GPT 1, 2, and others could do. But also it can solve classification tasks as text-to-text, and it is the main idea on the first step, how people start to optimize previous versions of architectures, and how people started to create something useful for all the types of tasks. Let's talk about second step for involving new tasks, how people developed something new, and these new things which people created, how they involved on a wide range of tasks which large language models can do right now. So Bloom is a powerful multilingual LLM with 176 billion parameters developed as a part of the Big Science project to promote open research, supporting 46 natural languages and 13 programming languages. Bloom is designed for both linguistic diversity and technical use cases. Let's talk about some technical details and architectural details. So Bloom is a decoder-only transformer with 70 layers and a hidden state size of 14,336. It uses 112 attention heads to process a language, making it highly capable of handling complex linguistic structures. To manage its massive scale, Bloom incorporates several optimizations. Let's look on this part of the slide. So firstly, it's mixed precision training by combining half precision and bplot 16 formats. Bloom conserves memory while maintaining performance accuracy. Also, the zero redundancy optimizer reduces memory usage by disturbing model states across GPUs, essential for handling 176 billion parameters. And also they used leverages this library, Megatron Deep Speed Library, for efficient distributed training on hundreds of NVIDIA R100 GPUs, ensuring faster and more stable training runs. There was a question in the chat. Let me see. Okay, it's just somebody says hi. So okay, let's yeah, here we can see some detailed changes what was in the Bloom architecture. Also is attention with linear biases and variance, which in short we can name alibi, which adds a fixed bias to attention scores and linearly decreases with token distance. Let's talk about Bloom corpora. It was trained on the roots corpus, a dataset containing 1.6 trillion tokens. This corpus includes content from diverse domains, multilingual documents, scientific papers, quote, and public domain text, such as diversity equips Bloom to handle texts in multiple languages and specialized domains. And what we can see in the Bloom was which changes was the second step of developing large language models. In my opinion, it's firstly size of this architecture. Also, it's decoder only architecture, which involve us to say that this is one of the most robust architectures, and we can see here that here we have multilingual corpora and also languages of code. Yeah, and it is wide range of multilingual of languages in the same time. So also one of the most important changes, in my opinion, is size of corpora on which they trained this model. And we can see a trend that people started increase size of the model. People started increase data soft of the model in I mean count of tokens in the corpora. And also they wanted this model to be optimized, and in this case they started to use mixed precision. They started to use techniques for memory optimization and other stuff. So yeah, I think if you haven't got questions, we can move a little bit to the next to the next architecture. And and the next architecture is PALM. In the long name of this model is path-based language model. PALM is a major innovation by Google, consisting of up to as we can see here 540 billion parameters. It's quite big, and it's leveraged the pathway system, allowing it to scale efficiently across thousands of TPU chips. TPU chips, it's similar to GPU, but but not the GPU. So it's Google chips. And what we can see, which changes we can see in the Palm. They firstly, they used Swiglu. Its activation function instead of the commonly used relu. Swiglu combines the swish activations with gated linear units. This activation function enhances model expressiveness and improves gradient flow during training, helping Palm capture more complex patterns in language data. Also, they used rotary positional embeddings. Is a technique Palm uses to handle positional information more effectively. Unlike absolute positional encodings, ROP applies rotations to query and key vectors. I had a picture here. How does it work? So in the rotations to query and key vectors in the attention mechanism. And this allows the model to keep track of positions while maintaining flexibility for varying sequence lengths. And this is practically useful in tasks require longer context, as it allows Palm to handle extended sequences without losing positional information. And also, Palm's training utilize Google's pathways technology, which allows the model to be distributed across 1,000 TPU cores. Pathway facilitates efficient resources use and parallelization, optimizing the training process for such a large-scale model. Also, Palm was trained on the variety of data sources, including including web pages, as how we can see here, books, GitHub repositories, and social media content. With few-shot learning and Palm can adapt to new tasks by seeing only a few examples, demonstrating impressive generalization capabilities in reasoning the problem solving. Also, they used chain of thoughts mechanism. It's a way how, if a few-shot mechanism is the way on how we can prompt model, we can show it a few examples of the tasks, and then it will solve the third task that is look as the previous by understanding what people want from it. But here in chain of thoughts, we can prompt model not only when in the structure when we not only show use cases in the previous context of similar tasks. We can say here to think how it can solve this task. And here on the visualization, we can see that we just can say the model to make a chain of its solves, and it will think for a while. Maybe it will generate more tokens, but at the end, it will generate the right answer. Besides, based on that thoughts that was created in the generated text moments. Did you get this information, or should we explain it in more details? Also, did you understand what is few-shot prompting? Okay, good. So yeah, and I want to make some conclusions of this kind of model. It was the third step of evaluating, of developing large language models in that view that we have today. And here, what we can see, firstly, it had a huge size, as we can see here, and these sizes of models are similar to sizes of large language models. Here was the smallest sized 8 billion parameters, but right now the smallest no, okay, the smallest size right now in 2024 in the end is 1 billion, but we started from 7 billion parameters when large language models created, and we can see that there is changed of positional encoding, which allows us to see long context of the model. We had some tricks with models in T5 architecture when we used, let me go to that slide, but when we used a relative positional encoding, this one, and it's increased context size too. But this type of positional encoding is useful right now, and we have it in the large language models. Also, we see changes, some architecture changes of activation function. Also, it's still decoder only transformer. And the most important thing, I think, it's chain of thoughts. Chain of thoughts useful right now in large language models, and it's very impressive way of how we can prompt models. Okay, let's move to the last type of architecture, and I think it is the last step which we will discuss on this lecture, but we will continue in 1 week what have changed from Flan T5, and we will make some conclusions of all the changes and development of to large language models, and make some conclusions of what was happened on this way of creating large language models. So Flan T5 is a variant of the T5 model, specifically fine-tuned with instruction-based learning, and it's very important to understand this. FLAN, which stands for fine-tuned language, extends T5's capabilities to better follow instructions, making it more effective in tasks requiring structured responses. And let's move to okay, let's move to Flan T5 architectural details. It uses the encoder-decoder architecture of T5, but includes instruction tuning, which is unique to this model. By training on data sets that involve instructions, Flan T5 can handle tasks requiring specific prompt-based responses. And also, Flan T5 is available in various sizes. It's the smallest version has 60 million parameters, and XSL versions has 11 billion parameters. This range allows users to balance between model capacity and computational effectiveness based on their requirements. And let's deep to training details. It's involves training all large on large data sets where each example includes on explicit instruction. This improves the model's ability to follow directions given in natural language, making it more adaptable to specific tasks. And also Flan-T5 incorporates several techniques from T5, such as GLU activation, the Gaussian linear unit activation function inches the model's nonlinear capacity. Also relative positional encoding, about which I told you on the previous slides. It's allowing to handle longer input sequence and adapt flexibility to varying text lengths. Also, it used layer norm and span corruption pre-training. This improve stability and help Flan-T5 generalize across different types of tasks. Flan-T5 was trained on an expanded set of datasets covering natural language understanding tasks. Its datasets like SuperGLUE and Squad to anxious question answering, text generation tasks, datasets such as CNN, Daily Mail, for summarization, and VMT for machine translation. Also, there was reasoning tasks. Examples include NLI dataset, Logi-QA, preparing the model for complex logical resourcing, and coding tasks, including code exclude, human eval, equipping the model to generate and evaluate code. The most important changes in this type of the model is instruction dataset, which allows model to follow instructions in the moment. We will deep a little bit to this change in the beginning of next lecture. But in the short, it is just follow the detailed instructions, how model can, in the same way of chain of thought prompting, it can not think, but follow detailed instructions in its prompt on the pre-training. And this detail rely on quality of the model in the end of its training, and allows us to do to extend amount of tasks which can solve our language model, and increase its quality. And let's here we can we have usage examples of Flan-T5. It's solving reasoning tasks, multilingual NLP tasks, text generation from instructions, and question answering. So let's recap key points of this lecture. we explored some of the most influent large language models. An encoder model focused on understanding context. As an example, we can say that it is BERT. A decoder model built for generation. It's GPT, Bloom, and Palm. Encoder-decoder models that unify tasks under a text-to-text approach with specialization in instructions following as FLAN T5 and the previous stage of these models, T5. And also large-scale multilingual and multitask models that push the limits of computational power and linguistic diversity. As an examples, we can say that it's Bloom and Palm. In the next session, we will dive deeper into large language applications. We will discuss, we will recap key moments, what people changed to develop large language models. But right now, we can summarize the information that we firstly increased size of the model. We increased tokens on which amount of tokens we pre-train our models. We added long context. For example, we did with rotary positional encoding. And also we developed some unique strategies how we can train the model following instructions or and prompting it as a result on chain of thoughts concept. These key details got the one step further to go to the quality of large language models and chatbots in this moment. So do you have some questions for this lecture? So many large language models, their tasks are similar. Did you have to choose a model for your principal problems? How did you approach selecting one with another? Okay, if I will answer this question, if I answer this question in 2 years ago, when we hadn't got large language models as Llama, and we had only huge only amount of these models which we discussed today, I say that we can choose model rely on the size of this model which we can use in these tasks. What would be useful if right now we have more techniques for inference large language model in a simple way, and big size of the model is not a huge problem right now. But sometimes to have a more efficient result, we need to model what will be more optimized. And sometimes if you want just classification task, it would be useful to choose BERT language model, and work with it. But if we have resources and we have time for the inference of model, we can choose, for example, FLAN T5 if we need next token prediction, and because it follows instructions, and this change in this FLAN T5 architecture allows us to have better quality of the model. But if I will tell you right now how to choose the model, you can just look in the leaderboards and look for the benchmarks that you need. For example, you know the task, what you need to solve. You have benchmarks on the you can see some leaderboards on the Hugging Face, which I showed you on lessons, and you can choose a benchmark. It's a data set on which is similar to your tasks, and look on the metric of quality of the model. If you need to inference a large language model or just a language model on specific tasks, which is similar in this benchmark, you can rely on the metric, which model is higher, you can choose it. Is it clear? Okay. Yeah, thank you for your question too. Okay, more questions? Do you have more questions? Okay, if not, thank you so much for your attention. Thank you for your questions. If you will have some more questions, please ask me in the chat in Telegram. And have a good evening. Yeah, goodbye.